Let's talk about pressure. Pressure is predicted by kinetic molecular theory. And here again, we need to get a little bit into physics. Pressure is the result of the collisions between the particles in a gas and the surfaces around them. Because of pressure, we can drink through straws, we can inflate basketballs, we can move air in and out of our lungs. I think that's probably the most important of those three things. We can breathe because of air pressure. And variations in atmospheric pressure create wind, and changes in pressure help us to predict weather. That's why the weatherman's so hung up on high and low pressure systems. That helps him predict what's coming, because that's what causes variations in the weather, is these high and low pressure systems. So what is it about a gas that makes it exert a pressure? Well, pressure in general is defined as force per unit area. So force is something hitting something else, it applies a force. And when you divide that over the area, you get the idea of pressure. So you think about, this analogy changes every time, and sometimes it works out better than others. So why does it hurt so much when you step on a Lego barefoot? So when you step on something, your weight is actually a force. So let's say you weigh, 120 pounds. 120 pounds, and when you step on your bare foot, what is the area of your foot? Maybe half a foot squared, I don't know. But there's a fairly large area. Does it hurt the bottom of your foot when you apply that amount of force on the floor? No, we walk on our feet all the time. And unless, you've got bad feet or arthritis or something, your feet generally don't hurt. Bad shoes can make your feet hurt. But just walking barefoot doesn't hurt. When you step on a Lego, especially like if you get it right on your heel, Legos are small, right? Now, all that force of your body is not spread out over the entire area of your foot. It's on that little tiny piece under where the Lego is. Does that hurt? Yeah, that'll send you through the roof. Have you guys never stepped on Legos barefoot? It's like the worst. It's a tie with goat heads. Those little pokey, thorny things, and they just jab into your skin, and you just jump through the roof. So that analogy didn't work out very well at all. Oh well, it's one of those days. So pressure, actually let's write this out. Pressure is force divided by area. So pressure equals force divided by area. So if you have a big force over a big area, the pressure might not be very great. It could be 1. If you have big force over a tiny area, the pressure is going to be greater. On linoleum floors like this, it's actually possible to punch holes in the floor wearing stiletto heels, because the area of a stiletto heel is maybe a 1/4 inch squared, and you put the force, let's say 120 pounds, and you divide that by 1/4 of a square inch. What does that even end up being? It's 120 times 4, right? Oh, my calculator, where are you? So 120 divided by 0.25. That's a pressure of 480 pounds per square inch. That's a lot of pressure. And it's not because the force is so great, it's because the area is so tiny. The area is so small. So here we've got gas particles. They're very tiny, and their force is very tiny. So each of them is exerting just a little, small amount of pressure. Small force, small area, not a lot of pressure, but there's a lot of them. And they're hitting the sides over and over and over again. And the pressure of the gas is going to depend on several things. One of them includes the number of gas particles in a given volume. The more particles in here, the more pressure, right? Because they're going to be hitting the walls more often. So few particles, low pressure. Lots of particles, higher pressure. Pressure imbalance has many applications to everyday life. If you've ever ridden an airplane or taken a drive up to like Kings Canyon, you notice that your ears do funny things, right? They make popping sounds. And if you've got a cold or some congestion in your head, it can actually cause quite a bit of pain. What happens is your ear has an eardrum, and that separates the outer ear from your inner ear. And there is air inside your inner ear, and there's something called a eustachian tube that connects it to the back of your throat. Well, if everything's working correctly, as you go up into the mountains, the pressure outside goes down. Atmospheric pressure is lower at higher elevations. And then the pressure inside your ear is still the same as when you were down here on the valley floor. If your eustachian tube is working properly, it'll open up and let that pressure out. If it isn't, it will cause your eardrum to bulge out. That doesn't feel good. When you hear that popping sound, that is the sound of your eustachian tube opening and letting the extra air out of your ears. And then when you come back down, the opposite has to happen. I don't know about you, but for me, coming down never works as well as going up. I thought there was another picture. When you come back down, then the pressure inside is less. The pressure outside becomes greater and greater and greater, and it causes your eardrum to bulge the other way. And this is why babies often scream on airplanes, because their ears are killing them. Air pressure. Pressure is something we can measure, so of course we need units. The simplest unit is one that we use a lot in chemistry. It's called the atmosphere. It's abbreviated ATM. And this is the average atmospheric pressure at sea level, 1 atmosphere. The SI unit is a Pascal, which is 1 Newton per square meter. We don't use that one very much in chemistry, but there it is. I told you about it. The Pascal is a much smaller unit. 1 atmosphere is 101,325 pascals. You don't need to memorize that. We do need to learn how to do conversions with pressure units, though. Another pressure unit seems pretty strange. A millimeter of mercury. That sounds like the length of an element, right? Well, it kind of is. And this unit has historical significance. So this is an illustration of the original mercury barometer. Torricelli used one of these. I think it was back in the 1600s, maybe? I could be wrong. Anyway, he took a glass dish of mercury and a glass tube full of mercury, and he inverted the tube into the mercury, and some of the mercury came out. And what's left up here is a vacuum. What he noticed was, whenever he did this, the height of the column of mercury was always the same. It was about 760 millimeters tall. Well, that's something that's easy to measure. All you need is a ruler. You can make this with a fat tube or a skinny tube. It doesn't matter. It's always the same height. That was interesting. You wonder how people get these ideas. He took it up the side of a mountain. Why would you carry a thing of mercury up the side of the mountain? For one thing, it's really heavy. But he did. So he took it up a mountain, and he noticed that as he climbed the mountain, the level of mercury, the height of this column, got lower and lower. And then when he brought it back down, the height of the column of mercury went back up again. Because what's happening here is atmospheric pressure is pressing down on this pool of mercury, and that's what supports the mercury inside the tube and keeps it from coming out. My kids like to play with all kinds of stuff in the bathtub, right? And so, they've got cups and bottles and all kinds of stuff in there. And so you take one of those red plastic cups, red Solo cups, right? And you fill it up with water under the surface of the bathtub, and you tip it upside down, and you lift it up, and the water stays in the cup. as long as the bottom of the cup, like this tube of mercury, is under the surface of the bathtub water. The water doesn't come out. But then when you pull it out farther, whoosh, all the water comes out at once. Why does the water stay in the cup? It's because of atmospheric pressure pressing down on the bathtub water. It can support a column of water. The column of water could actually be 34 feet tall. Column of mercury is only going to be less than a yard, 29 inches long, because mercury is much more dense. It's much heavier for its unit volume than water is. So this was how atmospheric pressure was originally measured, as the height of a column of mercury. In fact, you see that kind of funny yellow strip on the wall over there? There used to be a mercury barometer there. And it was fancier than this. It had a built-in ruler and this little thing that you could look at the level with. But it was this same idea, a long skinny tube of mercury with a dish of mercury at the bottom. And you could read the atmospheric pressure with the barometer on the wall. So at average atmospheric pressure at sea level will support a column of mercury of 760 millimeters. That's equal to 29.92 inches. And that would be converted just by converting millimeters to inches. So here's a useful table, common units of pressure. There's a mistake. Hopefully they fixed it. I think if you've got version 5, edition 5 of the book, hopefully they fixed it, because they had the wrong unit here before. That's why I fixed it in red. But all of these units, Pascal, atmosphere, millimeter of mercury, torr is exactly the same size as a millimeter of mercury. And this is a unit that was named after Torricelli, who is the developer or the inventor of the mercury barometer. So that's the same as a millimeter of mercury. Pounds per square inch, or inches of mercury. The way these tables are set up, all of these are equal to each other. So we don't have to go doing multiple step conversions. We can do pressure conversions in just one step. I would encourage you to memorize these down here, because you're going to use them a lot. 1 atmosphere is 760 millimeters of mercury or 760 torr. Yes?
Isn't it 29.92 inches of mercury maximum vacuum that can be done on Earth?
I'm not sure what the maximum vacuum. I'm not sure how low they can get it. I have seen it get pretty low though. So let's do something, a conversion. Convert 173 inches of mercury into pounds per square inch. So let's just go back and look at that table to get the factors we need. Oh wait, I skipped a slide. And I meant to write on this slide. Okay, you should memorize this one. Right there. And then the slide I accidentally missed. Convert 1.25 atmospheres to torr. So here's our table. What we're going to do is we're going to look for, here we have unit of atmospheres, and we're going to torr. We're going to look for the one that says atmospheres, that's this guy, and the one that says torr. And notice that both torr and millimeters of mercury, those are exact. So when you use the number 760, it is an exact number. It is not just two significant figures. And these are all equal to 1 atmosphere. This would also be exact. We're comparing all of these to 1 atmosphere. So these numbers, 1 atmosphere is equal to 760 torr, is the conversion factor we need for this first example. So 1.25 atmospheres. And we're going to multiply by torr and divide by atmospheres. This is dimensional analysis again. This is 1 atmosphere. We put a 1 in front of the atmosphere. 760 torr. And then we use our calculator and we take 1.25 atmospheres times 760, divide by 1, and we get 950 torr. How many significant figures should that answer have? It should have 3. So that's not the best way to write it. Thank you, Train. So that's the best answer, 9.50 times 10 to the 2. Any questions? Here's another one, 30.15 inches of mercury is equal to blank millimeters of mercury. So let's identify the conversions that we need. Millimeters of mercury is 760, and inches of mercury is 29.92. Those two are equal to each other. You can take any two number unit combinations from this table, and they'll be equal to each other. So 30.15 inches of mercury times, we want to put millimeters of mercury on top and inches of mercury on the bottom. And we look at the numbers over there. We've got 760 millimeters of mercury and 29.92 inches of mercury. So 30.15 times 760 divided by 29.92. And how many significant figures should this answer have? It should have 4, because 30.15 has 4 sig figs, and 29.92 has 4 sig figs, and 760 is exact, so we don't have to worry about him. So this is going to come out to 765.8. 765.8 millimeters of mercury. Question? You could. In my book, scientific notation is never wrong. So that would be 7.658 times 10 to the 2 millimeters of mercury. When we've got zeros to the left of the decimal point, that's when things can get a little tricky in terms of knowing whether it's significant or not. Any other questions? Let's do this one. Let me refresh my memory. 14.7. So here we've got 173 inches of mercury, and we're looking at pounds per square inch. So from the table, we can look up that 29.92 inches of mercury is equal to 14.7 psi. That's our unit equation. So we start with 173 inches of mercury. All of these are going to be one step, which is really nice. We're going to psi, so we're dividing by inches of mercury. Inches had the 29.92 in front of it. Psi had 14.7. 173 times 14.7 divided by 29.92. How many sig figs for this one? 3. So my calculator is showing me this. 84.9966, and it just keeps going. 3 sig figs, what should I round this to? 85.0, and then the unit is PSI. Because we're going to keep 3 digits, 8, 4, and 9. We look at the next digit, it's 9. That rounds this one up. Rounds it up to a 10, which rounds the 4 up to a 5. But we need to put the 0 there because that 0 is a significant figure. Any questions?